All right, class, this is just a brief explanation about where the Taylor's remainder theorem or Taylor remainder inequality comes from. This is just mainly conceptual about what the thinking is behind it. So let's just start with very basic. Suppose we've got a curve and we're trying to approximate it at A, and we could, if we just approximate it with a constant, maybe C, so this value is C. Well, what's the worst case scenario if we, on an interval? So if we have an interval that goes from here to here, we'll say this is over D and this way and over D this way. Well, one way to figure out what's the worst that this could be on that interval is if we have a constant, then we can look at how fast the function changes from that constant. And if we find out how fast it's changing on this interval, what the maximum value is of that on this interval, then we can assume that worst case scenario. So so right here it looks like maybe the steepest slope is right here. So the slope on that interval tells us how fast the value is changing away from the constant. So if we start here and assume we are always changing at this rate, then we get a line that maybe looks like this. And notice I'm higher here and lower here than my actual function. I have to, because I found the quickest, I found the highest rate at which it's changing on that interval. So if it changes sometimes lower than that, then it can't reach up to this level and it can't get down to this level. And so the most we could be off is this distance here, which is, we have a slope of whatever this is, we'll call the slope S. So S times the distance of D. And D is the distance, if we call this is A, this is like, if we give this an x coordinate of x1, then D is equal to x1 minus A. So that's S times x1 minus A. So either of these will give us the maximum value that we could be off out to x1. But you can actually do the same thing with if you're approximating it with a line, then so here's A again. Here is here we're over D, so this is A minus D. This is A plus D. We could call this x1, and we could call this maybe x naught. So suppose we've got a function again, but suppose this time we're approximating it with, instead of a constant, we'll approximate it with a linear function. Okay. So it's going to be a better estimate. Well, how far off could we be? Well, we just have to look at our original function and look at the curvature, look at the concavity that's the most around here. Look at the acceleration. What's the largest the acceleration on this interval from here to there, and then assume that acceleration everywhere. So maybe the biggest acceleration is right here, and so then if you assume that, then the most we could be off is, let me pick a different color. So I'm accelerating away from this blue line. So I might do and I can do positive or negative acceleration. So if I'm down here, I'll just assume a worst case scenario of something like that. So now the worst case is, this is the worst case we could get over here, and this is the worst case we could get over here. And this is a quadratic, and so how much is that? Well, you're going to have like your x minus a squared, because it's quadratic. It's the acceleration. We have we'll call this capital A for acceleration, the max acceleration here. And we do have to divide by 2 to keep that max acceleration in check. The same 2 comes from making sure we're matching the second derivative, because when we do the power rule with this 2, it's going to divide out. And so I can do that up to x1 or down to x0. And you can start to see a pattern here that if we find the max of the n plus first derivative, and we take x minus a for the usually it's an end point, but for some value on a given interval, then, and here we end up with n plus 1 factorial, ends up being the same pattern that we talked about before when we're taking that the power rule. Then this is the furthest we could be off, and it comes again from thinking about worst case scenarios. What's the worst case we could come from? We could draw this the other way too. I mean, we could take this and whatever the acceleration is, keep the slope there and move away from that slope, have the slope change with that max acceleration, and then this would be our max value, or this could be our max value, and that has to be more than what our function is actually away from. So I hope this makes sense. You can see now where we look at the next derivative to see how far the nth derivative could be moving away, and just assume worst case scenario. So we find the maximum of the n plus first derivative on this interval, and then assume it moves at that rate, and that's where we get that formula with the fn plus first of x on the interval. Have to maximize that. It's usually an endpoint, and then you have your x minus a to the n plus first factorial with the m. Okay, hope that helps. Thanks.